used. Low alloy ferritic steel has been widely used in steam piping, specifically in conventional power plants, and specifically in the UK. High temperature crack growth is of great concern in these components, as intergranular creep cracks can develop along the boundary between the heat affected zone and the parent material. We need to study the creep crack growth data and the creep crack initiation in these weldments and parent material interface. Creep crack growth data was provided by EDF Energy from ongoing test programs on both half CMV and parent material. And we looked at the ASTM E1457 standard to correlate the crack growth data with the C-star parameter. In addition, we also looked at the creep toughness parameter at given crack extensions of 0.2 and 0.5 millimeters. This is because it is widely used in the EDF Energy R5 procedure in the time-dependent failure assessment diagram to predict creep crack initiation times. Segments of normalized and tempered half CMP pipe were used to fabricate a weldment joined by 2 1/4 chromo weld metal. Coarse and refined HAZ microstructures were produced on the opposite sides of the weld by a predetermined weld bead deposition method. Compact tension specimens were extracted the parent specimens were extracted in the pipe axial radial orientation, and the HAZ specimens were extracted in the weld transverse radial orientation. The thickness of the specimens was 25 millimeters. However, due to size limitations, the specimens had to be reduced from the standard width of 50 millimeters to 47 millimeters. The specimens were pre-fatigue cracked, and a Sharpie V-notch profile cutter was used to induce a notch of 10%. And they were all tested at constant load at 540 degrees. So the procedure outlined in the ASTM E1457 correlates crack growth rate with the C-star parameter. In this equation, D and phi are material constants that can be both stress state and material dependent. Experimental C-star is determined from the load line displacement data by this equation. Here, eta is taken as 2.2 and h is determined from the power law exponent. And in addition, the standard also outlines a validity criteria. There's 3 criteria that have to be fulfilled. First, you have to ensure that global steady-state creep conditions have developed ahead of the uncracked ligament. And for this, we look at the transition time, which we evaluate at different data points, assuming small-scale yielding and plane strain conditions. And we take the maximum of this, and when the transition time is exceeded, we can assume steady-state conditions. Secondly, we look at the load line displacement rate, which is dominated by creep. So for creep ductile behavior, we ensure that the creep load line displacement rate is at least half of the total load line displacement rate. Note that in this analysis, creep and plastic displacements have not been treated separately. That is to say that we calculate the creep load line displacement by subtracting the instantaneous elastic load line displacement from the total load line displacement rate. And the third criteria is the crack should have initiated by 0.2 millimeters. So we're expecting to correlate A dot with C star. We expect the tail region where the crack is initiating due to primary effects and damage accumulation, followed by steady state region where we can correlate crack growth rate. We also evaluate the creep toughness parameter, and this is associated with time, temperature, and crack extension. We look at the load displacement data and we evaluate the plastic area in the load displacement curve at load up, and we use this equation to calculate it. Moving on to the results. In all these charts, P denotes the parent specimens, F denotes the fine grained specimens, and C denotes the coarse grained specimens. Over here we have crack length normalized by specimen width against normalized time. And here we have displacement against normalized time. You can see that minimal crack growth is seen for 80% of the test duration, followed by accelerated crack growth until failure. Parent specimen 2 specifically shows faster crack growth rates towards the end of the test. Next, we look at the validity criteria. The majority of the data fall within the creep ductile regime, where it's above half the total load line displacement rate. All invalid points are shaded gray, including those for which crack growth is less than 0.2 millimeter and the transition time has not been exceeded. And you can see that specimen P2 has failed in a creep brittle manner. Then we correlate the crack growth rate with the C-star parameter. We can see that for a given C-star, that the crack growth rate in the fine-grained specimens is higher than the has specimens. We also fitted a separate regression line to the data to calculate the parameters D and phi. We normally expect a phi value of below unity. However, in this case, we have not obtained it. And this can be attributed to the tails that are still apparent in the valid data. So that brings the question if 0.2 millimeters is a good place for crack initiation. Next, we look at the creep toughness parameter. The creep toughness at both 0.2 millimeters and 0.5 millimeters. The creep toughness reduces with test duration for long-term tests, and it, in the has specimens, is reduced by approximately a factor of 2. And this we can compute into the time-dependent failure assessment diagram to predict crack initiation times. To conclude, the procedures in the ASTM E1457 have been followed to correlate the crack growth rate with the C-star parameter. However, a phi value of below unity was not obtained due to the tails still apparent in the data. The crack growth rate in the has specimens were generally higher than those in the parent specimens. The fine-grained specimens were seen to exhibit higher crack growth rates than the coarse-grained specimens, and the creep toughness parameter was evaluated, and we found it lower for the has material than the parent material. However, further work is required to correlate the creep crack growth rates and see how they compare with the NSW models. We're awaiting specimens from EDF to work out to calculate the creep ductility. Thank you.